This is video 24 in the series on videos concerning concrete slabs. We will talk in this video about general principles of strut and tie models. Take a beam with a span of L simply supported and the depth of the beam is H. The beam is loaded with a uniform distributed load, and when the span of the beam is bigger than 3 times the depth of the beam, then there will be a compression zone on top of the beam. There will be a tension zone on the bottom of the beam. And when you compare stresses, then you will see that the blue is the compression stress and the green is the tension stress. So this stress distribution is valid around the middle of the beam, and all concrete tables are created for this situation. We call this zone the B zone from Bernoulli. It's the Bernoulli zone because a section before loading stays a section, or a plane before loading stays a plane after loading. But when you are in the vicinity of the supports, then the compression strut makes this movement, and we do not know anymore how is the stress distribution, and all existing concrete tables are not valid anymore. We call that the D zones or discontinuity zones. Now let's look at a beam where the length is smaller than 3 times the H, so the whole zone is a D zone. And the normal stress distribution is not valid anymore, so what will we do? That's why the method of strut and ties are developed. First, some general definitions. When you have a foundation block loaded by a column or a force P, and the reaction is taken by 2 piles on the left and the right. This zone, the blue zone, is the compression strut. It's a strut. The tension zone on the bottom is the tie between the 2 struts. And where the strut and the tie is coming together, we have a node. Consider a force P taken up by 2 piles, not symmetrically, then with an angle θ1 and θ2, then we know that this force P on the left-hand side can be decomposed in N1, T1 and P over 2, and in the other side the same thing, P over 2, N2 and T2. The relationship is very simple. The reaction force is of course proportional to the distance of geometrical distances, L2 over L times P. The same for the reaction force on the other side. The normal force in the strut is the reaction force R1 divided by the sinus of θ1, and 2 is R2 divided by the sinus of θ2. And the tension T1 is the reaction force R1 divided by the tangents of this angle. And it's also exactly the same as the reaction force on the other side divided by the tangents of θ2. These are general principles that we will use throughout the videos. So now let's look again at the foundation block for a symmetrical configuration to make life easy. Then we see that for the column load P, the normal force in the struts is P over 2 divided by sinus theta, and theta is the strut angle. The tension force in the tie is then P over 2 divided by tangents theta, and from this tension force, we can directly calculate the needed reinforcement in the tie, which is just the force in the tie, tension force in the ties divided by the yield strength of the steel. Something about the nodes. The nodes can be anchored really mechanically by an anchor. It can also be anchored by an anchor length of the reinforcement bar. You can also bend it up or bend it horizontally, like here. Anyway, the rebars making up the tie should always be anchored sufficiently after this point, which is the intersection of the strut and the reaction force. It should be, after that point, sufficiently anchored. Considering a node where two struts come together with the acting force, we consider the surface omega 0 equal to the distance A times the width of this foundation block or whatever. So it's A times C, and omega 1, this one, the surface here, is of course B times C. The reaction force in the strut is then P over 2 divided by the sinus of theta. And we see that B times the sinus of theta equals A over 2. The strut angle is theta, and we see in this triangle here below that the sum of the angles are 180 degrees. So we have x plus, this is 90 minus theta, plus 90 degrees. So it means that x is theta. So this angle is also theta because this is theta. Then we can see that the stress on this section, omega 0, is the load divided by omega 0. It means the load divided by A times C. And if we now substitute A, which is 2B sinus theta, then we got 2B sinus theta times C. And then we see immediately that this is P1, because P over 2 times sinus theta, P over 2 times sinus theta is P1. And then omega 1 is of course B times C. So this is equal to P1 divided by omega 1, but P1 divided by omega 1 is exactly the stress on this side of the node. So it's sigma 1. So sigma 0 equals to sigma 1, and the same for sigma 2. So this means that this node is hydrostatic. It's the same stress on all sides. For the struts, the maximum allowable stress, compressive stress in the strut is 0.6 times nu times FCD, and nu is 1 minus FCK divided by 250. For a node in compression, strut and reaction force, then the maximum allowable concrete stress is K1 nu FCD, and K1 is 1. For a compression node with only one tie, so there is a compression force, reaction force, and one tie, then the maximum allowable compressive stress in the node is K2 times nu FCD, and K2 is 0.85. And then finally, the compression node coming together with several ties, then K3 is 0.75, and the maximum allowable stress in the node is K3 nu FCD. The maximum allowable stresses, they may be increased by 10% when the angle of the strut is more than 55 degrees.